All right, so now we coming up for the last session of this first day. This has two talks, both given by scientists from the Indiana University Information Technology Services. The first of the talks will be given by Justin Miller, who will tell us some practical issues about doing I/O on TeraGrid-related facilities such as the data capacitor. Thank you.
Good afternoon, everybody. Hope you've enjoyed the talk so far and were able to catch the keynote this morning. So let's get started. So I thought Alex Saleh did a good job identifying some key challenges for data-intensive scientific computing in his keynote this morning. Mainly that scientific data is doubling every year, higher fidelity sensors, and a higher speed sensors is increasing the amount of data that you need to work with. And in fact, the amount of data is becoming a barrier to extracting knowledge from the data itself. So he identified at the end of his talk that the problem of today is data access. So one of the questions we can ask ourselves is how can we minimize data movement? So I'd like to look at some example research workflows to bring home some points to researchers here. So in this workflow example, you've got a data source that could be any instrument. It could be from a microscope. It could be from computational simulation. Anything that you can think of, just think of it as data. So that data is transmitted and stored on your computer. And in this simple workflow, there's one compute resource. So you transfer your data to the resource, you run your job, you run your simulation on the data, and then you transfer it back to analyze what you've done. Pretty simple workflow. And works well for gigabytes, maybe even a terabyte, if you're patient. In a slightly more complicated workflow, you have the data source again, where the data is stored on your computer. You transfer it to a compute resource, you run your simulation or your job, get the results back. And maybe there's another compute resource that has slightly more, or it might have proprietary software that you need. It might be a different architecture that you've written your code for, but another compute resource is another transfer. And an even more complicated workflow, you've got the data source, compute resource 1, compute resource 2, and now maybe visualizing your data is not possible on your laptop or workstation anymore. And maybe you want to use a visualization resource, which leads to yet another transfer. And finally, after all of that, you visualized it, we still haven't dealt with archiving your data to tape or some permanent home for your data. So you can see a lot of arrows here, a lot of transfers, and it's starting to get cumbersome. It's starting to get in the way of actually doing science. So you can see that with 4 resources, it's starting to get out of control. It's starting to become unsustainable. And like I said, it might work for gigabytes, maybe even 100 gigabytes if you have fast network connections, maybe even terabytes if you're really patient, but certainly not much more than that. Certainly not tens or hundreds of terabytes, which some data sets are becoming. Every resource that you add is another transfer, and it's starting to get in the way of you doing work. But there are very good reasons to add these resources. So certainly there shouldn't be a penalty for adding resources to your workflow. And we haven't even addressed other drawbacks, such as data integrity or version control. IU provides a central file system that we call the data capacitor. And a central file system sits in the middle of this workflow. So you see we've moved your computer out of the workflow, and now your data is written once and stored on a central file system where the data comes from the source, can be used on the compute resource, another compute resource, can be archived, can be visualized, all without moving your data again, which is a key to progress in science, is getting the computational, getting to it as quick as possible and reducing the barriers to using your data. So the IU data capacitor file system at IU was funded by the National Science Foundation in 2005. We bought 535 terabytes of storage, and we used the Lustre file system, which Rob Latham talked a little bit about in the previous talk, and I'll come back to again. And we provide 339 terabytes of that to researchers at IU. So the name data capacitor comes from the idea of a capacitor in electronics. So a capacitor in electronics is a basic building block, and it provides a storage of electrons and evens out the flow of electrons. So one side coming into it can be intermittent or slow or fast, it doesn't matter, but the output of it is always reliable and consistent. So it's kind of the same idea, and we're using that as a model for this central file system. The data can come in from anywhere, but when you're actually using it, it's reliable and consistent and fast. And it's centralized for IU resources. So you can store your data on the data capacitor, you can compute against it on the compute resources, use the same space as scratch space because it's really fast, and we intend it for short-term storage. So we think about 2 weeks, a month before you need to find another home for your data. There is a possibility for longer-term storage, which we call project space. So if you need to use the same data set a lot, but move the results off, that could be accommodated. So the data capacitor at IU is central to IU resources, and those resources include IU supercomputer Big Red, which is a 40 teraflop IBM machine. There's a general purpose compute cluster called Quarry, which has some high memory nodes in it that's also useful for analyzing and computing on. And the data capacitor is central to IU resources, which also includes HPSS, which is a name for a hierarchical storage system that moves your data to tape eventually. So it's a permanent home for your data that you can retrieve from too. This is a diagram of IU's cyber infrastructure. So you can see here's the data capacitor, and we're connected over 10 gigabit Ethernet to the core switch, which is also connected to Big Red, which is also connected to Quarry, which is also connected to HPSS. So it literally could not be any closer to these resources, and we're using 10 gigabit Ethernet, which is really fast. So some researchers at IU have made use of this centralized file system model, and one of those is Dr. Chuck Horowitz, who's interested in studying neutron stars and the behavior of nuclear matter and particle interaction. And his workflow is to run the simulation on some hardware, and in this case he uses MD Grape 2, which is some specialized physics hardware. He does some post-processing on the simulation results and then visualizes those results. So he's got 3 steps. So if we look at a diagram of his workflow here, we've got the data on the data capacitor. He computes on the resource, writes the results back, and then does some post-processing and writes those back, and then he can use a visualization resource and eventually write to tape and retrieve that if needs be. So we're kind of a one-stop shop for storing your data. And in this model, in this workflow, the data capacitor is central to what he's doing. And this is an example of what the visualization of his simulation looks like. So another project, an earth science research project that makes use of the data capacitor at IU is the Linked Environment for Atmospheric Discovery project. And they they participate in a competition called WX Challenge, where students, grad students, faculty, anybody that wants to compete can try to forecast the maximum and minimum temperatures, precipitation, and maximum wind speeds for a select city over 10 different cities over a 10-week period each semester. So they provide the data for the people that want to compete in this challenge. So they make use of the data capacitor too. So data comes in from whatever source. meteorological data, NOAO data, comes in, is pre-processed on a cluster in the computer science department that mounts the data capacitor over 10 gigabit Ethernet as well. Write it to the data capacitor. People that compete in the challenge can use IU's compute resources to make their predictions, their forecasts, and write that data to the data capacitor and can store it there. And then there's also transfer resources such as grid FTP where they can transfer their data to wherever they want. So again, making use of the centralized file system resource at IU called the data capacitor. So in our eyes, the data capacitor has been very successful, and we've been doing it since 2005. And the thought came up of how can we make this better? What can we do to build on the success that we've had with the centralized file system model at IU? So the natural progression of that is to be central to more resources, right? And IU didn't add new compute resources, but certainly new compute resources are being added nationwide. So if you want to be central to more things, you need to reach across the nation, and you do that by going over the network. So IU did this by extending the file system across the wide area network, or the WAN, and we created a new file system called DC WAN, or Data Capacitor WAN, and it's a new separate file system from the original DC. So now we're talking about two file systems, DC for data capacitor and DC WAN for data capacitor WAN. So the data capacitor is central to IU resources, and now the data capacitor WAN is central to nationwide resources. So over the network, we can use resources in San Diego, in Austin, in Kansas, in Urbana, Illinois, Mississippi, Tennessee, Pittsburgh. Anybody that wants to mount the data capacitor, we can work with them and do this over the network. So there are some trade-offs to doing this over the network. One is, a question? Sure.
Yeah. Your data capacitor is using Lustre file system, right?
That's correct.
Isn't Lustre very unstable?
Well, it doesn't have to be. I mean, the hardware that we have behind the system is very resilient, and there's redundancy built in. So if one piece fails, there's other pieces that take over for that. So in our experience, it's actually been quite stable. I think we've had over 96% uptime since 2005 for the original data capacitor, and certainly over 95%, 96% for the DC WAN since 2008. So it's been pretty successful for us. And there's tolerance that can be built into the system. Lustre itself is not inherently unstable. So if that answers the question. So data capacitor WAN, central to nationwide resources now. And okay, back to the benefits. The benefit is the illusion of locality, that on the resources in California or Texas, when you're on the machine at the command line, it looks like any directory that is in there or on the system. So there's no special commands that you need to use your data. It's just standard commands. So because it is over the network, your data is being transferred behind the scenes. And even though it looks like it looks and acts like any file system that's mounted on these compute resources, it is transferring your data over the network. So like anything that goes over the network, sometimes it goes slower than you like because there's congestion, you don't control the network, you're competing with other people. IU happens to be particularly well suited for WAN file systems because we have a great network infrastructure, and the data capacitor WAN is connected to the Internet 2, iLight, other high-speed research networks that don't get a lot of congestion. So you're able to use the DC WAN quite successfully. So here I say, at best, it's as fast or faster than the local storage sometimes. And typically we see comparable to local storage across the network. So you get the benefit of locality, or not having to manually transfer your data and not manage different copies of your data. You're not having to transfer. You can use your data on whatever resource you want by writing it once to the data capacitor. So one challenge for WAN file systems is heterogeneous user identification across sites. So because IU Data Capacitor DC WAN lives at IU, we have one particular we have a particular scheme for UIDs. So every user has a username and a UID. So inside in Unix, the kernel identifies you by the user ID. So your UID is different at different sites. That's pretty natural. So what gets complicated is when you're trying to use a file system at one site and another at the same time, who is the authoritative UID for this file? So one really cool thing that DC WAN does is that we automatically do this conversion for you. We do the mapping between UIDs. So there's a small chart here at the bottom of the slide. I hope everybody can see it. So at Indiana, my username is JUPMILLE, JUPMIL, and my UID is 648424. And you can see that other sites, for instance at PSC, my username is also JUPMILLE, but my UID is 43415. So UIDs are not the same across sites. It's something that the file system has to manage if you want to have this, if you want to be mounted at their site and manage this for the researcher. You need to map between UIDs, and our file system does that, which is pretty unique and something that was developed here at IU. And there's a patch for the kernel code that we've submitted to Oracle and is available to people if they'd like to see it. So I told you about Dr. Horowitz running the physics research using the data capacitor and the specialized physics hardware. So this is an updated workflow for that same researcher. And the Texas Supercomputing Center, TAC, brought online a system called Lone Star, very fast system, and worked well for his code. So he was able to move his data to DC WAN, which is mounted at TAC on Lone Star, and run a simulation there, and run faster than what he was running on the other hardware. So it's essentially the same workflow before, that he wrote his data once and computed against it and visualized it, except that now he's doing it over almost 900 miles, and he's doing it in Texas. Except the data is still only written one place, and he can still use the local resources over a fast network. So everything's connected over 10 gigabit Ethernet. So same workflow, now he's doing it across distance. The centralized file system across distance has also opened up some new possibilities for storing data at IU. This is a workflow for the WIYN telescope, which is a project or a telescope run by Wisconsin, Indiana, Yale, and NOAO. And they have a special instrument called the 1 degree imager, which takes gigapixel images of the sky. And it's in a very remote location. So there's limited power, limited space. They just don't have enough power and space to run their own cluster there. They have a small compute facility on site, but it doesn't make sense for them to be running their analysis there because of the constraints. So they're able to take the images, write them to data capacitor WAN, and then analyze on whatever compute resource they want that mounts the data capacitor WAN. So it's great for them because they don't have to run anything on site. They can use our compute resources and also archive to tape at IU or any site that offers that service. Another really cool project that uses the data capacitor WAN is the Center for Remote Sensing of Ice Sheets, CRESIS. They're studying the ice sheets on the poles, so on the North Pole and the South Pole, and they collect data in Greenland and Antarctica. And They use planes that have these special instruments in them, and they're flying over and collecting data and storing them on disks. Then they ship those disks to Kansas, University of Kansas, and read the disks and store the data there. And then, so it's kind of like the Large Hadron Collider model, that there's a tier 0 and a tier 1. So the tier 0 is they read the data that came from the planes. They have an authoritative tier 0 backup, or not backup, but collection of the data, which you want to keep separate from what you're actually computing against. So they write the data to DC WAN, compute here using Big Red, and then write to tape archive. And this is actually an interesting story, and kind of ties into the keynote this morning, that they weren't sure how they were going to get the data and how they were going to use it. So the idea of FedEx came up, and shipping these disks to us, and us reading them and putting them on the data capacitor. So we thought, okay, that might work, but let's try mounting the data capacitor in Kansas and writing the data to it first. And lo and behold, it's actually faster than writing to the USB storage media. So this is a great example of file systems over distance and data capacitor WAN, preventing or reducing the need for shipping disks around. Okay. Any questions, or is that just feedback?
Yeah, this is Notre Dame.
Hi, Notre Dame.
Hi. So what are the client requirements if you want to hook up to the DC to your DC WAN capacitor?
Sure. So Lustre is distributed under the GNU GPL. The clients are available for Linux. You just need to be running the Linux kernel with the Lustre packages installed, and then you can mount it over the network. The changes that we've made that do UID mapping and keep track of that for you are run on the MDS side, the metadata server, which I'll get to in a little bit. But for the clients, you can use the stock distribution of Lustre. So just my email address is at the end of the presentation slides. You can email me, email the data capacitor team, and we'd love to talk to you about getting the data capacitor mounted at Notre Dame. I've mentioned a lot of TeraGrid sites. TeraGrid money paid for the data capacitor WAN, but we've successfully mounted at non-TeraGrid sites, so University of Kansas, Mississippi State University, also mount the data capacitor. So we're all for anybody trying to mount the data capacitor and using it for science. Okay. So one more workflow, and this one's actually pretty interesting because it really makes use of the file system over distance. We have a friendly user here, Scott Michael, who's a astronomy PhD at IU, and he's interested in gas giant planet formation and has code to simulate the formation of these planets. So his workflow is to write the initial data that he needs to run the simulations on DC WAN. Then he logs into Pittsburgh Supercomputing. They have a machine called Popol, which is an Altix 4700. It's an SMP, large shared memory machine, which is what his code exploits really well. So he logs in there, he runs a simulation, and writes the data back to DC WAN. And I think his simulations are on the order of about 20 terabytes. So having to transfer that data there, run the simulation, and transfer back would just really take too long and be impractical. So he's able to keep his data on DC WAN, compute on Popol at the Altix 4700 at PSC. NCSA, the National Center for Supercomputing Applications, also has an Altix 4700 SMP machine, so he can run his simulation there too, also using his data on DC WAN. So he runs the simulations at these sites. And just on a side note, this is actually kind of a great way to manage resources. So if you're a TeraGrid user, you're aware that you have service units, which are kind of the imaginary money that allows you to compute for a certain amount of time on TeraGrid resources. So his jobs run for so long, and he uses so many cores that he would easily run out of service units at one site if he didn't have more than one site to use. So Data Capacitor WAN, great for him managing service units. So he runs his simulations on the different sites, writes the data back to DC WAN. Then he can use a visualization resource to tell if his simulations are doing what he wants, or what he expected, or along those lines. And actually, since the data is being written to DC WAN and the visualization resource also mounts DC WAN, he can, while the simulation is running, look at the results that are coming in already and see if this simulation is going in the right direction, if he needs to stop it, if he needs to restart it with different initial conditions. Really, really powerful that he doesn't have to waste a bunch of time running simulations he doesn't need, that he can analyze it while it's going on, which is really cool. So simulations, write data back to DC WAN. He can do some post-analysis on the simulations at a different site. He happens to use Mississippi State University, who have a new supercomputer that they're bringing online. IU has a really friendly relationship with them, and they mounted DC WAN on their new supercomputer and allowed Scott to use it for free without service units. So it's been great for him. Once the data is back in DC WAN, just like all the other workflows, he can write to tape if he wants. And I think this is an example of really maximizing utility with DC WAN. So I actually have a small demo of the gas giant planet research that Scott runs. Just to set up this demo a little bit, the data is already on DC WAN, and DC WAN is mounted on Popl, and it's mounted on a machine here at IU in the astronomy department that has some proprietary software called IDL that Scott uses to post-process and visualize the simulation results. So let me go ahead and get this started here. So okay. In this window, this terminal window, I hope everybody can see it. If you can't, speak up now, because I'm going to go forward. We're logged into Popl. We're going to qsub into the debug queue so we can run our code right away. Great, we made it. We're going to go to DC WAN, which is mounted at /in/DC WAN. We have scratch directories for every user of DC WAN, so mine is scratch jupmil, and then I'm going to go into demo code. Okay, so if we look at the files here, we can see that they are owned by the UID 43415. Okay, so I'm logged into Batman here, which is an astronomy machine here at Indiana. I'm going to go to the same directory, /in/DC WAN /scratch jupmil /demo /code. And if we do the same ls here, you can see that it's the same files here owned by UID 43415, here owned by 648424. And I know this seems really simple, but it's actually really hard and something really cool that we've done. So I'm going to keep harping on it because we did it first. Okay, so I'm going to go ahead and run the demo code here. So this is a Fortran code using the OpenMP library that Rob talked a little bit about earlier. It makes use of the massive amount of memory on this machine. So just like any good cooking show, we're going to put it in the oven, but I've actually got it cooked already. So we're going to go over here, and we're going to go to the demo directory. And so we assume the code ran, output the results on DC WAN. Now we can run IDL to visualize the results. and we'll run the demo here. So this is making images from the data, and then it's going to make a little movie that we can watch. So like any good cooking show, I've done this already, so we can go ahead and watch it. So I go, this is a third window, also on Batman, connected over the network. Okay, so job runs on Popl, OpenMP runs the simulation, writes the data to DC WAN. On Batman IDL, we run the code, it's rendering the files into images, and then it'll combine the images and make a little movie. Third window, we've got the movie already, so we'll go ahead and play it. So, pretty pictures, real data, pretty cool stuff. All without moving our data once. We used two different resources. We could have used more if we wanted to. Okay. Okay, so that was the demo. Fun stuff. And the whole time we've been using Capacitor WAN Filesystem, also funded by the National Science Foundation. We purchased the hardware in 2008. We have 339 terabytes of storage available as a production service to TeraGrid, IU, non-TeraGrid users. It's a centralized file system, just like the Capacitor. This slide looks really similar because the Capacitor and DC WAN are very similar, except DC WAN is going over the network. It allows you to use the data as a resource that fits your needs. So in Scott Michael, the astronomer's example, he needs a large SMP machine. He needs a lot of memory, a lot of shared memory. So DC WAN allows him to use the resource that fits his research needs the best. Just like the DC, this is for short-term storage. The possibility exists for mid-term storage. 339 terabytes. After listening to Alex's keynote this morning, doesn't sound like very much. It's really meant for doing computation, getting the results, and doing something with them, not meant for indefinite storage. So DC and DC WAN are both based on Lustre. Rob talked a little bit about it. I didn't know he was going to, otherwise I might not have included so much information about Lustre in my slides, but it's a parallel distributed file system available under the GPL, not only used by university HPC resource providers. It was developed with help from the US government to fit their needs. Also used by movie studios, financial institutions, oil and gas industry. Anybody that you can think of that uses massive amounts of data probably uses Lustre. 7 of the top 10 HPC systems on the top 500 list as of June 2009 used Lustre. And in 2010, 52 of the top 100. So some people might think that Lustre is unstable or erratic, but other people are using it quite successfully. And the reason that people use it is because it scales really, really well. Tens of thousands of clients, petabytes of storage, gigabytes per second of I/O throughput. Whatever hardware you have, Lustre will make use of it. It does this by separating the pieces of a file system into dedicated servers, and together you get aggregate performance out of separating. So the cool thing about Lustre, maybe Rob might disagree, but one thing I think is cool is there's the standard POSIX file system interface. So what that means is that it looks and acts like a standard file system because it is, even if you're doing it over the network. So I kind of alluded to this earlier, but this example is kind of to point out that it really is a standard directory. So at IU, DC WAN's mounted at /n/DC WAN /scratch. I mean, that's my directory on IU. My directory at PSC, same. TAC, same. NCSA, the same. And because it's a POSIX file system interface, you can use ls and cp and cat, any of the standard Unix utilities from the command line. You can use it because you don't have to do anything special to get to your data on this file system. So some of the pieces that Lustre that make up the Lustre architecture are the metadata server, which is what stores the file system metadata, such as the file names and directories and permissions of the file system. It's responsible for the operations such as open and close. And then there's the object storage servers, which do the bulk I/O transfer between clients. So in a small scenario, a client says, I want to create a file. It tells the MDS, I want to create a file. MDS tells the OSS, you're going to create a file. And then once the MDS tells the OSS to create the file, the client can start writing to the OSS. I know this sounds a little complicated. I have a diagram to help explain. And in the back end are the disks, or the object storage targets in Lustre language. And this is the actual physical disks or RAID hardware that store the bytes. So this is a diagram of a generic Lustre file system. So here's the client, here's the metadata server. There's one of them. It's single. There's a single metadata server. There can be multiple OSS servers, and then there's multiple OSTs, they're object storage targets, which are the disks behind it. So this is where the speed and scalability come from, that the client is communicating directly with the object storage servers, which have many OSTs. So if you write one file, a very large file, it's not going on one disk, it's going on multiple disks. It might even be going across multiple object storage servers. So this is great for if you have a single processor doing serial I/O. It can read quickly across the object storage targets. Or if you have many clients doing, or many cores doing parallel I/O, they can be simultaneously reading files, and you're not blocking, and there's not a single connection to the disks. That you can read many files at once and be sending them to many different processes. So here I'm talking about the data capacitor, the original data capacitor. There's 16 servers, or 8 pairs, and I alluded to this a little bit in the question that came up, but there's 16 servers and 8 pairs, and they're in failover. So if one fails, the other one can take over its resources. So there's no single point of failure in the object storage servers. They are connected to the network over 10 gigabit Ethernet. We use fiber channel to connect to the storage hardware, 4 gigabit fiber channel. We're running Red Hat 5 with Lustre 1.8, and we use the Data Direct Networks S2A 9550 controllers. Data Capacitor WAN, very similar, less servers, less hardware, still very fast. Also connected over 10 gigabit Ethernet. So if I've sold you on using Lustre, here's how to get the most out of it. Lustre is optimized for large files, and we have a 1 megabyte block size, so we consider large files anything larger than 1 meg. So what this means is if you write a 4K file, you're really writing 1 meg, so you might as well take advantage of that and write the full 1 meg. And we're not very good for small files for that exact reason, that there's a lot of overhead for reading small files. Lustre has aggressive client-side caching, so if you're reading the same files a lot, that eventually you're reading from cache and you're not reading from disk, which is pretty common. But so the last point here is Lustre allows you to control how your data is striped across the OSTs, which is Lustre language for disks. So so you can control how many stripes there are, which can really improve your performance. And depending on the I/O model of your code can really increase the throughput for you. But there is a threshold that once you cross it, you actually have so much overhead that you're competing against yourself. So if you talk to the data capacitor team or email us at the end of the presentation, we'd love to help you optimize your code for Lustre. So Lustre WAN future plans. We are in the process of testing being mounted on the India and Sierra Future Grid clusters now. We think Future Grid is really exciting, and we'd love to have our service available to researchers using Future Grid. The DC WAN project has been pretty successful. Don't ask me, ask the TeraGrid, because there's a new project coming online in development that's using the UID mapping Lustre code that we developed here at IU for a Lustre-wide a TeraGrid-wide Lustre project. So I kind of ran through my slides here. I was a little bit nervous, but I'd love to answer any questions anybody has. Please feel free to contact me or the data capacitor team that runs the data capacitor at IU. We'd love to get DC WAN mounted where you're at.
Question from UCLA.
Please, UCLA.
Can you please explain how you did the UID mapping?
Okay, sure.
Your code,
Okay, so if we look at the Lustre file system architecture here, the metadata is stored on the metadata server, and it is actually the thing that's aware of what the UID is. So inside this client request, there is a UID so-and-so wants to do this operation. So we modified the MDS code to unpack the request, look at the UID, and depending on where it's coming from, so there's an IPv4 address that's inside of the request. So based on the IPv4 code, IPv4 address and the UID of the request, we have a binary tree in kernel memory that looks up the site, looks up the UID, and says, okay, this UID should act like this UID. So we fulfill the request, and then before we pack the response and send it back, we do the reverse map. So the MDS is aware that it's translating the UID, but the client is never aware of anything going on. So that's why we can use the standard, or the standard distribution of Lustre, because we don't change the client at all. It's only inside the MDS kernel code that this mapping is done. And for DC WAN, we use Indiana University's UIDs as the authoritative UID. So if a researcher has an IU account and an account at PSC, when the request comes from PSC, it's unpacked, converted to the IU UID, request is fulfilled, repacked, and sent back as the PSC ID. So it's pretty cool. I hope that answers the question. I can go into more detail if you want. So,
Just one more question.
Sure.
Thank you. So you said that you have 8 pairs of Dell PowerEdge machines. So is it the thing that you have one half that's running continuously and the other half are left idle and only use when some machines are down?
That would be true if we were in an active-passive configuration where half are passive and just waiting for something to fail. But we're actually in an active-active configuration. So all 16 are being used, except that we're using half of their capacity. So when one goes down, it can take over another half and be at full capacity. So there are 8 pairs, but all 16 are running and sending data at the same time. There's just some built-in capacity to take over for one that fails.
Yes.
Minnesota has a question.
Please, go ahead.
Chris Goodman in the Twin Cities. I'm interested in the applicability towards Lustre on lead node systems, such as Mac OS. Since Lustre is dependent on ZFS and since there are licensing issues out there for ZFS right now, are there any plans to help make it available to other file systems or help it bringing it to non-Linux systems?
Okay, there's a couple. First of all, there were plans for Lustre to be based on ZFS because it was owned by Sun and it was a natural marriage. But in fact, those plans are still in development, and Lustre right now uses the ext3 file system. But it doesn't really answer the rest of your question because there are only Linux clients at the moment.
A Mac OS 10 client's in development.
Okay, so I'm hearing a Mac OS 10 client is in development. So, yeah, I admit I don't know what the plans are for non-Linux clients, but rest assured that ZFS licensing won't be a problem. And that, in fact, Lustre is slightly file system agnostic. It just happens to use ext3. Except that ZFS is much more complicated than most file systems, so that's why it takes so much work to take advantage of all the ZFS features. So I hope I answered your question. If not, I can follow up.
UCLA has one more question.
Please, UCLA, go ahead.
I wonder what's the difference between the DC and other grid data grid system like the OGSA DI or the SRB. So I don't know what the difference is.
Okay, so the DC or data capacitor, the original one, is a central file system at IU and is not unique in that fact. It's just that that's what we built DC WAN on. So other sites do have central file systems, and in fact Lustre file systems. So as far as the data capacitor goes, it's very similar to central file systems at other TeraGrid sites. DC WAN is unique in that it's mounted at other sites and is doing this UID translation, which I think is unique in TeraGrid. Sorry, actually, GPFS WAN were the first people to do a WAN file system, but they're not doing the UID translation. So, so if there's any other questions, please go ahead. Okay, there's a question from Indiana here.
Yeah. Can I ask how many mounting points are there in total?
How many what?
Could you come up and please answer the question on one of these mics? Here's a mic.
Okay, there's a question from Indiana. We're getting a mic right now.
So the question was, how many mounting points are there in total for DC WAN now?
Oh, mounting points. Oh, it changes, but I think we're at 7 of the 11 TeraGrid sites, plus at least 3 non-TeraGrid sites. So we're up to 10, and Lustre is becoming increasingly common. So if they have a local Lustre file system, they have the kernel modules in place and can mount DC WAN. It's just a matter of getting the administrators to mount DC WAN.
So the UID translation part is actually just like converting the UIDs within those 10 mounting points.
Yeah, any site that mounts the DC WAN, we work with the administrators and say, okay, this user at IU matches this user at the site, non-TeraGrid or TeraGrid, and then we can do the mapping. So there is a little bit of pre-work that goes in to the UID translation at different mount points, but it's not too hard. It's pretty easy.
Okay. So could it be a bottleneck once there are more mounting points, like hundreds or thousands of mounting points? So
yeah, hundreds or thousands. I mean, it could be. I don't know how many large resource providers want to mount us, but it certainly could be tens or, 30. No, I don't know how many there are that want to mount us, but we certainly could scale to that.
Okay, so tens, no problem.
Yeah, tens, no problem.
Okay. Thanks.
Sure.
Hello, Nikhil. Also has a question.
Okay, go ahead.
Right, it's a two-part question. The first part.
I'm sorry, I'm getting a little feedback. I'm sorry.
Is that better?
Okay, that's better. Go ahead.
Cool. It's a two-part question. The first part is in terms of the data that you're getting from the different science projects. Are those provided to you as text files or binary files as any specific format?
I'm sorry, what was the first part of the question? I didn't quite hear that.
In terms of the format of the files provided to you, are those given, it's a predefined format, or are they normal ASCII files, binary files? Doesn't matter.
Are you talking about the data that you use on stored on the data capacitor?
Yeah, the one that is given to you by the price. The raw data.
Oh, I think I am answering the question when I say you can store anything, binary, text, on DC WAN. It's just a file system. No special requirement.
There is really no parsing on your part in the system, right? All of the parsing is performed by the computational methods from somewhere else.
That's right. That's right.
That's great. Thank you.
Sure.
UCLA has one more question.
Please, UCLA, go ahead.
Oh, yeah. We were looking at your UID mapping. We think it is cool.
Thanks.
We have one more question.
Okay.
Does that add any extra latency?
Does it add any what?
Extra latency, because you have to interfere in between and process.
Yeah. So we actually have a paper coming out at the TG 2010 conference that specifically details how we created the UID mapping code here at IU, and it turns out that it's such a trivial lookup that it actually adds no penalty to the metadata operation. That we're looking them up in binary trees. The binary tree is super fast. There's really small numbers. It's really easy translation. So it does add something, but it's basically negligible.
Relative to the latency.
Relative to the latency of what is already going on.
CLA has one more question.
Go ahead.
Can you talk a little bit about the back end as far as the disks?
Okay, sure. We use Data Direct Networks, S2A 9550, which uses SATA disks. We can get about 2.4 gigabytes per second through each controller. And the disks are in a RAID 6 8+2 configuration. So if you have 10 disks, it's the capacity of 8, and there's 2 that are there in case 2 fail inside of that RAID configuration. So that makes up one OST, and each object storage server has 8 OSTs. So there's 48 disks per object storage server. So I think maybe that was enough detail, maybe not. There's more info on our website at pti.iu.edu/DC, and there's a systems information page that has more than you care to know, I'm sure. Okay, if there's no more questions, that's in one.
I'd like to thank Justin. He said he was inexperienced, but he sounded like an accomplished master to me, and we'll be getting him to give more talks in future. And so I think we should give him a very well-deserved round of applause.